And okay. Alrighty. So good evening and good morning, and well, almost good night to those of you who are joining from Europe. But welcome to this month's microTAStic seminar. So we have two really exciting speakers today. So we have one of our invited speakers from hot paper in micro and nanosystems engineering from the Nature Journal. So we culled through recent publications in the microfluidic space. And we ended up with what became a 3D printing session today. So you're going to hear a lot about 3D printed microfluidics. So to get us started off, we have Matt Poskus from Yannis Zervantinakis' lab at University of Pittsburgh, and he's going to give a 10-minute talk about his exciting work that was published.
Yeah, thank you for the very kind introduction. Let me just share my screen. And hopefully you're able to see everything okay. All right, thank you for the very kind introduction. My name is Matt Poskus. I'm a PhD student in the lab of Dr. Yannis Zervantinakis at the University of Pittsburgh. And today I'll be talking about some of my work on applications of liquid crystal display 3D printing in microfluidic models of breast tumor drug response. So microfluidics have several advantages over other assays in that we can better control gradients, have a more physiologically relevant response, and we can use smaller reagent volumes. We can also more precisely control the position and therefore interaction between different cell types. And this allows us to study complex systems such as the response of macrophages to environmental cues in tumors, and dissecting the role of paracrine interactions in vasculogenesis. And so these microfluidic devices often use PDMS, or polydimethylsiloxane. And so this material has advantages in that it's optically transparent and biocompatible and has desirable mechanical properties. And so these devices using PDMS are created using a soft lithography technique in which a master mold, which is typically SU8, is used, and the PDMS is cast into the master mold and then removed from that substrate, and then you have your microfluidic device. But these master molds are often made using photolithography, and there are some disadvantages to using photolithography in that it's expensive and time-consuming and requires specialized training and facilities, so clean rooms, in order to operate them. We're also limited in the types of geometries that we can make, and so we can really make like extruded 2D planar geometries. And so to overcome some of these challenges in the accessibility of these SU8 wafers, we're proposing to use 3D printed master molds, which are a lot cheaper and more accessible compared to photolithography techniques. But there are some challenges associated with these 3D printed master molds, and that there's limited studies on the biocompatibility of the resins used for these master molds, and there's no real standardization in the printing protocols for this. So the resin selection, the printing parameters are all left to the end users, so the researchers, to optimize on their own. And so the purpose of this study was to address some of these challenges, increase the accessibility of these 3D printed microfluidic molds. And so the printer that we used was an LCD 3D printer, the Frozen Sonic Mini 4K, which was really the intersection of cost and resolution. So this printer is now less than $350 US and has a resolution of 35 micron pixels. And so the way this technology works, this LCD technology, is that an LED light source emits UV light, which then passes through a liquid crystal display or LCD layer. This LCD acts as a mask to selectively let light through to create an image on the bottom of the resin basin. And so this image locally polymerizes the resin to form a printed layer. And so that process is repeated to form all the layers of your 3D part. And so our workflow consists of first 3D printing the molds and then performing a series of washing and post-curing steps before ultimately arriving at the traditional pouring the PDMS, curing it, and demolding it, as in soft lithography for the SU8 wafers. And so in order to demonstrate applications of this 3D printing technology, we designed 3 different geometries: the micro rail, a gradient generator, and a micro well geometry. But I'll focus mostly on the rail and well geometries today. And so we're able to then convert these CAD models into 3D printed molds and then cast PDMS in them. And then we can answer biological questions using these assays, such as studying drug response in 3D and studying the migration and invasion of different cell types. And so we first wanted to optimize the 3D printing process. And so we started with resin selection. And so the first question we wanted to ask is, are these resins compatible? Do they affect cell viability? And so to do this, we printed using 5 different resins. We printed a microwell geometry, and we cast PDMS and then cultured cancer cells in the PDMS from these different molds. And so what we found was that the PDMS from these 5 different resins all had similar biocompatibility. And so we selected the TR250 LV resin because it had optimal thermal properties compared to the other resins. And so we also wanted to ensure not only are the cells viable, but do they respond to stimulus the same way. And so to do that, we compared the drug response of cancer cells treated with paclitaxel in PDMS from the TR250 LV resin, and compared that to a standard microplate assay and found that the drug response was similar. We next wanted to explore how different printing parameters affected the quality of these PDMS. And so we started off with the layer height, and so we compared a 50 micron layer height to a 10 micron layer height. And so we used a technique called optical profilometry to basically reconstruct the surface of the PDMS and measure the variation or smoothness in that surface. And so what we found is when we look at different resins, consistently that when we move from 50 micron layer height to 10 micron layer height, that surface roughness is decreased. And so we use the 10 micron layer height for printing. We next wanted to investigate how different printing orientations affects the quality of the PDMS. And so we looked at 3 different orientations, a 55-degree angle from the x-axis, 29 degrees and 15 degrees. And so this angle matters because whenever you angle the part, the surface is kind of discretized into voxels, and this effect is sort of known as aliasing. And so depending on how the part is angled, you have different extents of aliasing. So at 55 degrees, you'd be going over 1 voxel and down 5, and at the other end, you'd be going over 1 and down 1 at 15 degrees. And so because you have less aliasing at 15 degrees, you should, in theory, have a smoother surface and have a higher, smoother surface quality. And so this is indeed what we see when we look at the effects on the surface smoothness, or the RMS. However, the surface quality isn't the entire story. And so while the 15 degree is a little bit smoother, we do see a little bit of distortion of the microwells compared to the 29 degree. And so ultimately we selected the 29 degrees to print rather than the 15 degrees. And so the next step was to characterize the resolution limits using these optimized settings. And so in order to do that, we printed lines of varying width, ranging from 1,000 to 100 microns. And we did that for both an SU8 mold and a 3D printed mold, and we compared the PDMS. And so what we found is that we can resolve features in the 3D printed with the 3D printer down to about 100 microns. And we also repeated that for both embossed and debossed geometries as well, so positive and negative features. In this case, we used hexagons, and so we found that we can again resolve with these hexagons down to about 100 to 120 microns. And so we next wanted to ask, given that we've characterized this, we wanted to ask whether we could culture cells in 3D and study their invasion and migration in a 3D hydrogel. And so using the micro rail geometry, we polymerized a collagen type 1 hydrogel in this green area, or the middle channel, and then we seeded cancer cells in the flanking channel, and we monitored their migration into the gel. And so we seeded cells, and then for 8 hours, we studied their migration into the gel. And then after 24 hours, we counted the number of cells that invaded. And so we used two different conditions, starvation medium and complete medium, or 10% FPS medium. And we monitored the migration and invasion. And so what we found is sort of what we expected, is that whenever we starve the cells, their migration speed decreases, the distance that they migrate decreases, and we also see less invasion of these cells into the gel. But we wanted to apply this to maybe a more interesting and more novel application in breast cancer. And so breast cancer is the most commonly diagnosed cancer in women, and there are about 290,000 diagnoses per year. Of these cases, about 15% of them are HER2 positive or HER2 amplified breast cancer. And a major challenge with this disease is drug resistance. And so fibroblasts could play a major role in this drug resistance because they're implicated in a variety of tumor progression mechanisms, including cancer cell proliferation and survival signaling. And so a few years ago, we showed that fibroblasts can secrete factors that protect these HER2 positive breast cancer cells from a targeted therapy called lapatinib. And so the question we were asking is, we wanted to explore the effects of fibroblasts on cancer cell drug response to this drug lapatinib in 3D. And so in order to do that, we used two different assays, the first of which was a microwell spheroid co-culture assay, in which we cultured cancer cells either by themselves or with fibroblasts in these microwells. And we allowed them to form spheroids for 3 days before we treated them with lapatinib and monitored their drug response. And so using this technique, we were able to form spheroids of just cancer cells or cancer fibroblast spheroids with different numbers of fibroblasts in them. And so when we looked at their drug response, we saw that compared to the monoculture, that there was less cancer cell death in the co-culture with fibroblasts compared to the monoculture, and we also quantified that. The other assay we were interested in is looking at examining the breast cancer drug response in a 3D collagen matrix. So we seeded cancer cells either by themselves or in direct co-culture with fibroblasts, and we monitored their response to lapatinib after 48 hours of treatment. And so consistent with the spheroid assay, what we found is that compared to the monoculture, there's less cancer cell death in the co-culture. And again, we also quantified this. And so in conclusion, we used liquid crystal display 3D printing to overcome some of the challenges with the accessibility of photolithography, and we demonstrated applications in migration, invasion, and drug response. These devices are biocompatible, and we can resolve features down to 100 microns. We also showed two different cases in which fibroblasts limit the sensitivity of breast cancer cells to a drug called lapatinib in two different 3D assays. And finally, if you'd like to learn a little bit more about this project, as they said, we recently published these results in Microsystems Nanoengineering. And finally, I'd like to thank my lab members and funding sources, as well as the organizers for this really wonderful and opportunity, and it's really an honor to be able to speak here. So thank you very much, and I'm happy to take any questions.
That for that great talk on also a great paper. So since we're at quarter past, what we'll do is we'll take maybe one question now. So if someone has a burning question. Oh, there's one in the chat right there. Daniel, we're going to take your question. Did you have any curing inhibition issues?
We did not. And so part of the, maybe I can go back to it. So that was the rationale for the post-curing steps. So both the UV post-cure and then thermal post-curing limited the extent of inhibition. So there was a paper that was published basically discussing this effect. And so by using the thermal post-cure, we didn't have any PDMS curing inhibition.
Okay, great. And so what we'll do is, Matt, you're able to stay on through the end of José's talk. So keep adding your questions to the chat. We will come back to them. We're going to switch over to José's talk right now and have a nice dynamic Q&A at the end with our two leaders in this field of 3D printed microfluidics. So I'm now happy to introduce José de Silva. So he received his PhD in analytical chemistry in 2001 at Sao Paulo State University. He completed a postdoc at in the Laboratory of Integrated Systems, and ultimately obtained his faculty position at the State University of Campinas, where he is today. And so he's an associate professor of chemistry now, and head of the Department of Analytical Chemistry at State University of Campinas, and does quite a bit of work in bioanalytical applications and separation technology. Today, he'll be talking about some of his work in developing novel strategies for producing lab-on-a-chip and microsystems with 3D printing.
Thank you, Julia, for the introduction. Let me share here. Can you see the presentation? Okay. Okay, thank you. Thank you so much for the invitation. So it's an honor to be here. I think this is a great forum of discussion of microfluidics and a worldwide forum. So thank you so much for inviting me to be here. So thanks to Cindy, Angela, and Julia for organizing this and for the invitation. So today we're gonna talk about something about 3D printing. Oh, I have to thank you, Matthew, for the introduction. So some concepts I can skip my presentation. But as said, I finished my PhD working on capillary electrophoresis. And capillary electrophoresis were promptly integrated to microfluidics because it is more easily to apply potentials and get separations in micro device using this technique. So I had interest in finishing my PhD to work with this microfluidic systems. Just a minute. Yeah, my first experiences on microfluidics were with using silicone devices. This is a silicone device. And after that, we moved to more low-cost device using lamination, more specifically with the polyester toner devices. After that, we start working with many different strategies to prepare micro device, PDMS-based soft lithography, CO2 laser ablation with polymetacrylate. Also combining different materials, paper materials and glass materials, PDMS. It is an example of a glass substrate containing electrodes and PDMS micro device or microchip, microchannels over these electrodes to get electrochemical detection. And this is in the middle of 2010s. And we moved from 2018 to work with strategies using 3D printing to prepare directly devices. So different from the Matthew's presentation, we are interested on prepare the whole device using 3D printing, not only the template, the mold. So this is two examples of device. We'll detail more in the next slides. So why I'm so excited about 3D printing? Because it's an amazing technique. It's additive manufacturing. Actually, we have many techniques combined with this concept of additive manufacturing. For example, you can use this approach to prepare really large objects. For example, this is a house printed using 3D printing. This is the outside of the house. The inside the house is really good one. The luxury house, actually. We can also have really tiny devices. This is a structure. The scale bar here is 1 micron. So this technique is a 2-photon polymerization. There is the possibility to prepare devices with details below 1 micron. So this is a statue over a hair and a statue inside the hole of a needle. So this is amazing. Also, multi-material printers are promoting some, really impact on the producing of implants. For example, this is a printed eye implant. From the first sight, it's difficult to identify this. One of these eyes is really 3D printed. It's amazing. And of course, this also will start to be introduced in the analytical device. This is one of the first demonstration of capillary electrophoresis, actually the gel electrophoresis, capillary gel electrophoresis separation on a micro device. And also we have to pay attention to the global market of 3D printing worldwide, really large number. So just a minute. So what the today challenges of preparing directly micro device? So it's still a little difficult to prepare a device with channel dimensions below 100 microns. We are achieving this now, but it's not so easy to fabricate this device. One issue is the biocompatibility of the materials with live system, for example, cells, as Matthew showed. Combining different materials is still a challenge, multi-material printing. And sometimes for optical applications, it's interesting to have a really transparent device, and sometimes it's difficult to get this yet. And also have a conductive parts, for example, in my area, capillary electrophoresis, we'd like to have electrodes integrated for electric field application and also for detection. So conductive parts is really a good idea to include in this device. But also our motivation, our group, is also develop some strategies and the device with the low cost, because sometimes here in the development countries, it's difficult to get money to prepare devices and now also apply this device in remote locations. So this is one of the interests of our group. So looking to the possibilities of 3D printing, we start to develop some strategies to get really tiny channels, to use microfluidic protocols using 3D printing. So probably today, most of the people are familiar with the protocols of 3D printing, but just to get a simple idea, we have a computer design project. So we draw the device on a computer and save this in a file that is a stereolithography file, or there are also other formats of files. We generate G code that basically is slicing of the device in different layers, and this code is sent to the printer. So the printer will interpret this code to layer by layer produce the device. Okay. So the first technique we used was the fusion deposition modeling. That is one of the most popular and also one of the most cheap techniques of 3D printing. In this kind of technique, I did not put an explanation slide for this, but we have a filament that passed through a heated nozzle, and this nozzle can be moved in a XY direction. So you deposit the fused filament on a surface, and when you finish this layer, you move the nozzle for some few microns and start the position of the next layer. So this is one example of the one on device. This is the project in a computer project, and if you can see here, we found that for this technique, fusion deposition modeling, we don't have a really high resolution. So we get better resolution printing open channels. So this is one of the things. And to close the channels, you need to put a substrate and seal the device against this substrate. And we found that some materials of 3D printing materials, for example, polylactic acid, you can seal this perfectly over a PMMA, polymethyl methacrylate surface. It's really difficult to remove the first layer of adhesion of PLA against the PMMA. So if you just positioning a substrate here of PMMA on the printer and print the device over this, you have the channel sealed in a single step. You don't need to get an additional step. And we use this strategy, this kind of design, to prepare a micromixer for different analytical applications. This is a micromixer. I think most of people are familiar with mixers in microfluidics. But here we also have a feature that is a detection window in this position here. And this detection window using 3D printing is really easy to adjust the height of the detection window. So depending on the range of concentration you have, you can use a larger path, optical path, for example, for diluted solutions. If you have a concentrated solution, you can use a smaller path, optical path. So you can adjust just the concentrations for your application. This is a photograph of the mixer just here on the confluence, and also far from the confluence, showing the mixing. Here is the same mixer, but using a fluorescence solution. So you get the fluorescence here on far from the confluence. So here you can see the difference between preparing the device completely sealed and on the top here, and the device prepared over the PMMA substrate. So you can see much clearer the channel inside the device. And here is a separation. You see that passing here. This is a fluorescent that's moving through the electric field for separation using capillary electrophoresis on this device. Another application, we applied this for detection of nitrite. So nitrite reacts with the grease reagent to form this colored diazo compound. And this has a kind of a red color. And as you are using the microscope, we have a color camera, so we can select the channel, red, blue, or green, to do the correlation. So if you, for example, look here at the green channel of the camera, it correlates really well with the concentration of nitrite on the solution. So you can use this device for this micromixer to determine or for the detection of nitrite. Another example is an exercise for total protein. It's difficult visually to see the color here, but this is a kind of pale blue of the solution. And this pale blue correlates very well using the red channel. So from 0.005 to 0.05, we can have a good correlation for the red channel. Actually, is the inverse of the intensity against the concentration here. This is for proteins. We also developed some assays for nitric oxide. Nitric oxide is a very interesting molecule because it is a part of many different metabolic paths. So we have interest on determining nitric oxide in our group. So to prepare a standard solution of nitric oxide, we use this kind of a reagent, the nanoate salts. In this case, is diethylamine nanoate. This hydrolyzes at a low pH to generate NO. And the NO can react with the fluorescent probe. In this case, here is DAF-FM, diacetate, and produce this derivative that is fluorescent. So this is we use a fluorescence microscope to excite the probe in 495 nanometers and get the emission in 515 nanometers. So here's the results for 10, 15, 25. We don't have more points because it's really difficult to prepare this assays. And this, of course, is directly proportional to the intensity using the green channel because the light is emitted in the 515 nanometers. And here I would like to take attention for the blank. You see here the blank is also fluorescent. So this is one issue that we have to work better in the future, is to develop some substrates for preparation of micro device using 3D printing, but with smaller background fluorescence, autofluorescence. It can be really good for optical fluorescence applications. Okay. So another application for the basically the same device, just a little smaller difference in the design. This is one interesting thing because it's really easy to modify the design and print another device. So in few hours, you can prepare another device for testing. If you do this using conventional techniques, for example, photolithography, you spend at least one day doing the new molds for preparation, and it's really much more expensive. So in this case, it's for the generation of nanoparticles or synthesis of nanoparticles. We work with the silver nanoparticles, also gold nanoparticles. The reagents change, but it's basically the same idea. You have a source of metal in one channel. We have the reductant in another channel. And Lucas was the guy that yeah, I forgot to introduce you. Yeah, Lucas Bressan was the guy that developed these experiments. Sorry. So Lucas discovered that if they put a plug of oil between the aqueous solution, the nanoparticles do not attach to the channel walls. So this was one of the problems with these micromixers, that the particles were attaching to the surface. So using mineral oil, this does not happen. Let's see here. So you can see here the one of the device. And one interesting thing is that as you can control very well the flows in the channels, we can also have the really control of the conditions of the synthesis. Also the temperature we can control very well. And we get a really narrow distribution of particle size. So if you can see here, it's a 5 nanometers plus minus 2 nanometers, 7 plus minus 1, 7 plus minus 1. So really narrow distribution. For gold nanoparticles is another synthesis, another temperature. The particles are larger, it's 34 plus minus 12. For example, 20 plus minus 9. So you can adjust the conditions to get the average size of the particles with a narrow distribution. This is really interesting by using microfluidics for synthesis of nanoparticles. Another application, we prepared some core shell nanoparticles, basically combining two mixers. So in one mixer, we introduce the gold nanoparticles. In another mixer, we have the silver source of metal that will be reduced over the gold. So you have a nanoparticle with the gold on the core and the silver on the shell. You can see the increase on the size of the particles. We can also see here kind of a new population of particles. And here the extinction coefficients of the particles synthesized. Here is the application for thiocyanate detection using these nanoparticles. So you include these nanoparticles on an electrode and also get the oxidation, increasing oxidation as the concentration of thiocyanate increases. So this is a square wave photometry, an application of the particles synthesized. Okay, moving a little. This guy, Professor Dozil Jesus, is a colleague here at the institute. So we share the lab and also share a lot of our research. And Heverson was a PhD student that developed interesting improvements on this previous works. So Heverson could make some modifications on the printer to get smaller channels using FGM. FGM is really difficult to get this 6.4 micrometers of width of channels. It's really difficult. And also, Heverson studied different depositions of the filaments to get more transparent device. So you can see here is a traditional printing and the new approach, getting much more transparent device. If I remember, the number is more than 80% of transparency of the device. The transmittance is 80%. So it's really nice for optical applications. But another very interesting thing of FDM is that if you get two nozzles or maybe more than two nozzles, we can easily combine many different materials. So as we are interested in develop sensors, and also specifically sensor for electrophoresis, so we use this feature to get a device containing here an insulator material. Is a PETG, a kind of a polyethylene glycol polymer filament, and also to get some conductive filaments. You have some options in the market actually to prepare these conductive electrodes. And if you see here, this is the design. So the electrodes is around the central channel. This is really, or I can say this is impossible to prepare using conventional lithography. You have to use many different steps to get this kind of complexity in conventional lithography. And using 3D printing is pretty easy to project and print the device. One nice thing with this FDM device is that after you finish the printer, you can use the device. You don't need a new washing steps or curing steps. You can use directly after printing. So this is the final appearance of the device. You can see here the microchannel. In this work, Heverson got a little smaller with microchannel. Here is 59 microns. And here the electrodes. These electrodes are for contactless conductivity detection. So in contactless conductivity detection, we apply one signal to one electrode and get the transmission through the channel. And the distance transmission through the channel is proportional to the conductivity between the channels. So if you are separating ions, when the ion reach this region, so we have an increase on the signal. So if the ions are separating in electrophoresis, you have this two separation. Here's the reproducibility for 5 devices, the calibration for the different ions. And here's another important detail, actually, that Heverson used a kind of purge area to change the residues, to eliminate the residues of the filament that stay on the nozzle, so you can clean and get a more I said without any damage device. If you don't take care during the process, you can get this kind of damaged device. You cannot use this. Okay, Matthew got some introduction about the resins, and thank you, Matthew, for the details. That I don't have the details of optimization of the process. I will show some results. So I'm gonna skip this, the functioning of this kind of printers that were already said. So the first device we prepared using GLP the printers was a cell sorter. We're interested on a device to separate different cells. So Emily worked on this device, and I was worried that we could not get a good transparency of the device. So I expected a much more better transparency in this GLP printed device than the FDM device. So this was one of the first device that Emily printed. So after some optimizations of the process, Emily got more transparent device. And you can see here that perfectly applicable to visualization of cells inside the micro device. This is yeast cells that you use as model just to try the visualization aspects. Okay, I think a good improvements were done in this kind of technique by the group of Brigham Young University that is led by Professor Adam Woolley and also Professor Gregory Nordin, that developed a new really high resolution 3D printer, GLP 3D printer. And in 2017, these guys got a machine that could prepare channels as narrow as 18 per 20 microns. That was pretty impressive for this kind of technique. And I remember Adam showing this in a conference, and I asked him, so if it's possible if it were possible, to prepare some kind of a strategy that is a circular channel around a central channel. And Adam, okay, we can try this. And this were 2015. And some years after, we got the final device using this idea. So we have here, this is the project, this is the CAD project. These were printed in this special printer. This is a Korea 3G. It's commercialized now. This is the computer generated device, and this is a real picture of the device. So we have here a central channel that is about 40 microns in size, and spiral channel around the channel. The spiral channel is larger, is around 100 microns. But you can see the really complex device. So the idea is to use this circular spiral device as electrodes. So after the device were printed, we injected gallium. Gallium has a low temperature of fusion, so It's around 30 degrees Celsius. So we inject gallium here and get electrodes for contactless conductivity detection. So here's a separation of nitride using this device. The device is really tiny. The separation channel is around less than 2 centimeters, so it's a really tiny device. Some calibration curve for nitride and application for the determination of nitride in saliva. So yeah, this is a really interesting device. So just to avoid the use of gallium, we also tried some kind of electrolysis deposition. This is silver deposition. This is not the final device, but just a test to get the addition of the metal over the different plastics. You can see the resistance is 20 ohms. It's pretty low resistance. So one of the ideas is to inject the solution inside the channels to get the metal deposited on the channel wall. So you don't need even to use gallium. That is a kind of a toxic metal. And also, we demonstrated in 2015, this is an example of hybrid device also. This is a PDMS device over a polyester layer that we can use actually electrolyte solutions as electrodes. So we can even use electrolyte solutions, filling these channels with electrolyte solution, and you get these electrodes coupled to the separation channel. This is really interesting. It's really cheap also. Okay, another interest of our group is to prepare some electrodes for amperometric detection. And in this case, the electrodes need to touch the solution inside the channels. And this is really difficult to prepare in micro device because the alignment of the electrodes makes a great difference in the results, even more if you use electric field for separation. So you have to take care with alignments. And the 3D printing, again, can be used to prepare this kind of grooves. And Brenda worked on this project. And Brenda filled these grooves with conductive pastes. The same paste, the same resin used for to print the device. Brenda introduced some carbon material in this resin, and you can prepare a solid material, conductive solid material, using basically the same material of the device, the printing device. So here is an example of the flow to prepare these electrodes. You can see the photograph here of the final device and the electrodes touching the separation channel here. And Brenda studied the conductivity of this composite materials, and we got up around 0.8 Siemens per centimeter. Is pretty impressed about this value compared to the values shown on the literature, except for the metal particle that's pretty much larger conductivity, 10 to 4, 10 to 5, but it's not bad compared to many other types of polymeric, for example, conductive layers in this reference. If you need some more information, these results are published, and also we can send you some more information about the reference here. Are passing fast. So this is more for the electrochemical people. So we do the voltammetry inside the channels. This is a cyclic voltammetry. This is a probe, electrochemical probe, the ferrocene methanol, and square wave voltammetry of the ferrocene methanol inside the channel. So this is has a great potential to develop electrochemical sensors. Brenda also worked with another machines, more cheaper machines. The layer thickness here is 15 microns for this Nova Fab, and we can show here in this curve. This is for applications, again, in electrophoresis, that the current is linear behavior against the electric field application up to 250 volts per centimeter. That's pretty interesting for a microfluidic device. So this means that the channel is smaller enough to dissipate the heat generated on the channel. So this is interesting. So we can use this device up to this electric field, 250. To here is start to create bubbles, is not good. In this device, in this printer, we have channels with 165 micrometers in width. Here is the electrode touching the channel. This is a photograph of the device. Here's another interesting machine. The resolution, XY resolution here is 12 microns. It's pretty impressive. This is the one device printed with this machine, and these machines are cheaper now, so it's interesting. So here again, the separation channel is around, the width is about 100 microns. Okay, another project in progress in our group is the integration of potentiometric sensors in these channels. Is one example. This is the potentiometric sensor for chloride. And one of the last examples and applications is the use of a multi-material GLP printer. So we have you can find multi-material printers using FDM, also inkjet printers. You have multi-materials, but GLP is more difficult to find. I'm not sure if there is any commercial GLP multi-material printer. There's some research developed, but not commercial. And our GM was to use a kind of a commercial printers, a kind of a model is a kind of commercial one that we just modified the tank, the vat of the resin to get this kind of inclination. So we have a tilt of the vat here. So we can introduce one material, print the layers with this material, tilt the vat, remove the material. We don't want to throw it away, so we recover the material to the tank, original tank. Wash the tank, insert the new material, and this steps is repeated for any layers of different materials you want. So this is some pictures of the process, but I have a video here. So they start printing. You print the material is inside already. So you remove the first material. Come back to the tank, to the reservoir of the material. You clean the device to remove the residues of the material. Inject the second resin. Is injecting. You proceed the printing for the next layers you want. And this, in this case, the process was finished. But you can also have different any layers you want if you adjust the number of reservoirs you have on the input on the inlet of the tank. So some examples here. This is two material device. Here we included fluorescent material in one of the resins. So this part here is fluorescent material. This one has fluorescent material and also phosphorescent material. So this is under room light. So this is under UV light. You can see the fluorescent and also the phosphorescent material, and you cut the UV light. You can see the phosphorescent material emitting here around the 500 nanometers is the green emission. You can also prepare some complex device, multi-material device. This dice here has flexible material. This is dark parts, rigid material, this clear parts, and also a water-soluble material inside the dies. You can see here 1, 2, 3, 4 different materials. You can also use conductive materials. So you can print your circuit board, for example, but you can also print some tracks for turning devices on or integrating some electronics to the device. And interesting, this is a flexible resin, so we can also have some kind of a flexibility of the device for applications, for example, under the skin sensors. And that examples for electrophoresis with electrodes, conductive electrodes. This is the design. This is the printed material. You can see the channel here. This is the photographs of the material, the channel and the electrodes. This is a complex device. It's a spiral, a conductive spiral around the central channel. So this is the design, and this is the final printed device. We're also now adapting some resins and procedures to prepare some monoliths inside the channels, or even some layers to prepare some porous layers. So we can also introduce porous materials to get more functional device. So I showed a lot of examples. So my idea in the future, I hope that will happen in the future, is to have a kind of a machine that you project in a computer, the device with the different parts, insulators, conductives, porous, I know any kind of hydrophobic, hydrophilic, and send this to the printer and get the device in a matter of minutes, maybe, who knows, at least 1 hour to get a device. And also that this kind of protocols could be used for mass production. That is starting to be used for mass production, actually. So some closing perspectives and remarks. So I think everyone is now convinced that 3D printing is really powerful for microfabrication. I showed some examples of our groups, but there are many others that you can find in the literature today. Many amazing examples. So micromixers using FDM, so you can adapt the protocols to use in a different chemical analysis, and also for nanoparticle synthesis. So integration of sensors in the microfluidics device is also a good perspective. I did not show this, but we can also prepare valves and connections, different connections using 3D printing. DLP 3D printing, for example, check the papers of Professor Adam Woolley, that he showed the integration of pumping and valves in a single printing process. So potential for applications in many fields, including clinical analysis, and also multi-material printing is now a reality. We can also find some good examples of integration of different materials. And just to finish the perspectives, so it's interesting that many of the printers now is very accessible. For example, this one is I don't want to advertise any company. It's just some examples that I got from the internet. So this is about for less than $500 for a 12K resolution machine. So it's becoming really affordable for any research laboratory. So there are some companies that are focused on the production of a device that can be applied on microfluidics. For example, this resin is to prepare molds. Matthew showed some optimizations, but there is some also commercial options if you want. So cannot forget to acknowledge all the collaborators. This is an old picture of the groups. It's difficult to get updated because it's changing all the time. But Professor Dozil here, that helped me a lot on the development of this research. And people that are involved on these works, Lucas, Heverson, Brenda, Fernando também also made some contributions. Emily, Thaisa, Elisangela, Fernando, and Daniela. And also the collaborators, Professor Adam Woolley from Brigham Young University, Professor Fethi Bejoui, and Professor Anne Varenne from Chimie, Paris Tech. Also, I have to thank you a lot, the funding agencies in Brazil, FAPESP, CNPq, and also CAPES. And finally, I would like to thank you again, Julia, Angela, Cindy, for the invitation, the Chemical and Biological Microsystems Society for this initiative. So thank you also all the attendees for the attention. So thank you so much.
Great, thanks for this fantastic talk. We've covered so many different things that one can now 3D print in terms of micro scale assays. So we'll see if maybe any of us are in the clean room in the future, right? So we have a few questions in the chat, and if you have questions for either speaker, please also add them in the chat. I'll start with one of the ones for Jose. Abdullah, are you still here? And would you like to? Oh yeah, I see you. Would you like to unmute and ask your question about bonding PLA to acrylic?
Hi. In the beginning of the slides, I think it was mentioned that the PLA and the acrylic were bonded very well. And I wanted to ask what procedure is followed using that to do that.
Procedure to prepare the device over the PMMA?
Yes,
yeah.
using the PLA.
Yeah, we bought really large sheets of PMMA and cut in small pieces using a CO2 laser. And the only procedure is to wash the surface with ethanol or methanol and put on the bed of the printer. And we print the device over the PMMA. So just this. Very simple.
Okay, thank you.
Awesome. Next, Jake, do you want to ask your questions for Jose first, and then maybe we'll start alternating between questions for Jose and Matt.
Sure, I'd be happy to. I was curious to hear about some of the challenges and costs associated with implementing high-resolution FDM printing in a lab that doesn't have the setup for it versus DLP printing. Because I know you mentioned that there are some commercially available FDM setups, but that the DLP is not as easy to do multi-material. Sorry, I should add that in the multi-material context. How hard is that to implement in a lab?
Well, you need to get a good person in electronics because you need to adapt the machine. In our case, we have a two-stepper motors that tilt the vat. So you need to control these movements and integrate this to the printer. So someone that needs something about electronics and programming, computer programming, to get this control. And for GLP is this. For FDM, I think some is more easy because there are some commercial options that combine, for example, one nozzle with that can combine it with two filaments, for example. There's some machines that combine multiple filaments and using one single nozzle. You have machines with the 4 nozzles that you just have to position on the different filaments. So it's more easier to get the multi-material. but the resolution is better in a GLP. So if you want a high resolution in FDM, you also need to reduce the nozzle diameter. You use the 0.2 millimeter diameter. And also Heverson made some modifications on the geometry of the nozzles, because in our printer the nozzle is more longer, and the difference of temperature from the heater and the bed is bigger, so you do not damage the printed part using this longer nozzle. So it's some modifications on the printer that you can get and use for more high resolution device. But you know, the resolution is not in an optimized case is not much better than the worst case in GLP. That's what I would like to stress.
Gotcha. Thanks for enlightening my on that. Thank you.
Alrighty, I think now Matt has a question for Jose.
Yeah, I was just wondering if you could maybe elaborate a little bit more about, I guess you had a slide on the high resolution FDM printing and how you're able to maybe, print those like 60 micron channels and improve the optical clarity. So I guess I was wondering if you could maybe discuss like maybe the optimization or what you would change to be able to do that. Because that's
Yeah,
really impressive.
thank you, Matthew. The answer is the same, because changing the geometry of the nozzle to get a longer one. So the difference of temperature of the heater to the bed is bigger. So the heating the already printed part can also cause some distortions on the device. So you can control much better the size of the filament that is being deposited. And another thing is the distance between the two filaments on the device. If you have some, void parts on the device, you get this effect of worse transparency, and more closer the filaments, or I can say less voids in the device, better is the transparency. So you need to adjust this kind of deposition.
Awesome. So I think we might be back to Jake again, who had a question during Matt's talk about thermal curing. Jake, do you want to ask your question?
Oh yeah, I just wanted some more specifics about the time and temperature that were used, and if you had trouble with the curing with any resins in particular. I know there can be a lot of variation in how effective the thermal treatment is depending on the resin and the geometry of the print.
Yeah, so we cured these at 80 degrees Celsius for 48 hours. And so some of the resins, I guess for different reasons, we had challenges. So, I had mentioned in my talk about how we selected the TR250LV because it had better thermal properties. And so some of the resins, their glass transition temperature is around 80 degrees Celsius. And so we had problems with deformation of some of the molds. So like the beige dental mold was not really rated for the temperatures that we were curing them at. And the nylon green, I'm not sure of the reason, but it did also seem like there was a little bit more curing inhibition in the nylon green compared to the other resins. So that was the only resin that we really had any problems with. But it wasn't always consistent. So yeah.
Right, yeah. I know that there can be a lot of variation with the effectiveness of that, and it depends a lot on the resin. So I've faced some of those challenges as well. And actually in our lab we've had some decent experiences recently using some coding procedures or trying to flesh those out a little better. But if you send your email in the chat, if I'm able to characterize that better and get that really effective, I can send that over to you, and that protocol might be of use for your future work.
Yeah, that would be great. I just put my email there. Yeah, and maybe I have a question for you if you don't mind. Sorry.
Sure.
Did you silenize the molds out of curiosity? Is that the treatment, or?
I did attempt that. Yeah, that was effective in some cases, but not all. What I found to be really effective was a particular variation of treating with acrylic. So yeah, I want to do some more tests and really make sure that that's effective before I go out on a limb and highly recommend it. But that's why I'll take your email and let you know if that's working really well.
Great, thank you.
No problem.
So I have a question for Jose. So for the devices where you mentioned including like carbon in the uh,
The
resin's not the
resin.
right word for this. Yeah. And then printing that. I'm wondering, do you ever see any challenges with clogging? That's just kind of the first headache I think of with the 3D printer. Kind of that I'm most familiar with using, and whether there's any unique challenges with clogging with
Yeah, in the first device, the channels were open, and Brenda just filled the side channel with the paste, and after this kind of sand, paper with a sandpaper just to remove the excess of the material, and make this with really care, not to put a material inside the channel, the fluid channel. So it's a kind of it's a hand job. It's really difficult to adjust. And in another one, that the channels were completely closed, already printed, closed, and the detail is to have the side channel with an area much larger than the fluid channel. So when you insert the paste on this channel, naturally it flows to the other part that has a lower fluidic resistance. So that's the idea. In some cases, if you have a much low viscosity material, of course, this low viscosity material can penetrate into the channel. So you have to protect this in some way. But if you use high viscosity materials, it's more difficult that you clog the separation channel. I don't know if I could explain it better.
Thank you. So I see we have a question from Carlos. Carlos, do you want to unmute yourself and ask your question?
Yeah, definitely. Yeah, and many thanks for the fantastic presentations. I guess it's just one quick question, more on the software and slicing sort of things. So are there any considerations being made during the printing process or before the printing process for the multi-material slicing, right? And software, or is it kind of done by hand, I guess, or is it pre-considered and optimized for multi-material?
That's for me the question.
Yeah, I guess either one, but yeah, more, yeah. Thank you.
I can start using, for example, FGM. You can select on the CAD software the different parts that can be sent to the printer. So it's more natural to do this. I never worked, unfortunately, with the inkjet printers. More expensive. We don't have this here at the Unicamp. But FGM is pretty simple to get this. In the GLP, you have problems because you have to stop the process and change the resin and start again. So you need to include some stops during the G code so you can change the resins. It's not manually, because you can include a routine to do this automatically, but you have to program this. Yeah, so it's a little troublesome to do this. But in terms of the layer, is the same for the conventional process. to adjust the layer for your best performance, printer performance.
Got it. Thank you.
Matthew, you want to complement?
I don't really have much to add. I guess the software that we use is Chitubox, and I guess as far as I'm aware, maybe it would have to be done manually. I'm not sure if there's any functionality for multi-material printing.
On that,
we have
sorry.
So
Sorry, please
we
go
have a
ahead.
compromise with the timing of the printing. So if you use a really tiny layer, so the printing can take hours. So sometimes you don't know, you don't want to wait so long for a print. Sorry.
Yeah, definitely. Yeah, that makes a lot of sense. It's only because recently somebody mentioned to us multi-material DLP slicer, so I was wondering if any of you had a previous experience with that or something.
No, I don't have experience. Yeah, I would
Okay.
like to have.
Yeah, same. Yeah, thank you.
If you have some information, you can send me, please.
Yeah, I definitely will. Yep, will do.
Alrighty, are there any lingering questions for our two speakers? If not, I'll just kind of pose something to both of you to close it out. So, what do you see as sort of the frontiers in 3D printed microfluidics? I have a sense of it from what you guys presented, but what do you think are like the limitations currently, and where's the field going? Are we all gonna do microfluidics and 3D printed devices in the near future? If so, how soon, etc.?
You want to start, Matthew?
Sure, yeah. So I think, there's some exciting research going on in terms of, I guess, a lot of our research focuses on using PDMS. And so, the resolution of printers is increasing very quickly. And so since we published this paper, they've already come out with, these 12K and 8K printers. And so, the resolution is really increasing very quickly. So that's exciting. But I think also what I've found interesting and really exciting is essentially the resins. So we can, I guess there are PDMS resins that maybe aren't commercially available, but there are some labs interested in or are working on those essentially. So the idea is that you can directly print using, the DLP or LCD printer, directly print PDMS. And so, that kind of combines the, some of the advantages of PDMS for the biocompatibility and with the flexibility and truly 3D power of 3D printing.
Well, I'm very optimistic about the future of 3D printing microfluidic devices because there are appearing some companies that is directed to the producing of microfluidic devices using 3D printing, also dedicated printers to do this. And I think in the future we'll have more options and cheaper options that do devices better than today with a lower cost. And also, I would like to just to complement this with the amazing technique that is two photon polymerization. And the problem with the two photon polymerization, that the resolution is amazing, but takes too long to prepare the device, and also is a really tiny area. So it's 300 microns per 300 microns. So this is not for the thinking about to prepare a whole device, but it starts to appearing machines in the market that combines the resolution. So you can get on the same machine, prepare a larger size device with a low resolution, and when you need high resolution, for example, a feature inside the channel, you can use the best resolution of the machine. So this is amazing. I think in the future we'll have some nice machines to prepare these devices directly. And also inkjet printing, that is also amazing. There are some companies that putting on the market some machines that can use inks with a really large variation of viscosity. So you can prepare your material, put there, and print the material. So I'm optimistic about this.
That's great. Thank you so much. I might have to ask you for the name of the company that that can do the large scale coarse resolution and also zoom into smaller area and do high resolution. But thank you so much.
Awesome. Well, with that, we'll wrap up our session for today. Thank you again to both of our speakers, and for this dedicated group of participants who've hung on this long to get every last morsel of detail they can get from you guys. So thanks so much for answering their questions. And we will see you all next month for. Is this that's the final microTAStic of this series,
yeah,
right?
Yeah.
Okay. Well, we'll see you next month. Thanks.
Thank you.
Thank you.